Okay, so welcome to Math349 Operations of Order. This should be a lecture, I think, 8. No, it's 7. It's no longer displaying over here. So what I want to do today is I want to talk about some of the Fibonacci stuff. So we've just had a couple of lectures where we have been looking at some questions in analysis. And the more real analysis the easier it's going to be to study questions like this. If you haven't seen real analysis, what's nice is if you now take that class, you'll have seen a lot of these concepts, and it'll be much easier the second time you see it. So switching gears, I want to talk a little bit about Fibonacci numbers. And this is for a book project that I'm working on where you guys will be able to come in and be authors of chapters that will be read across the world. And so I don't know how long it's going to take us to go through the stuff because I want to go through slowly so you have a sense of what is the mathematics that's being used, what could you be working on. And so almost all the results I'm going to talk about are results that were proven by either Williams students or students coming to work with Williams students. So these are all very accessible problems to students. For a lot of it, you don't need that much background. You just need to know what is the right way to look at things. And that is often, the greatest challenge, especially for something that you've seen, time after time after time, is can you find a new perspective on the subject? That's very hard to do. But once you can find that new perspective, I'll see since you can upside down. Once you find that new perspective, all of a sudden, you have the chance of doing calculations in a way that other people haven't. So it is entirely coincidental that there was, it wasn't there. It's entirely coincidental that it was flipping while I was talking about new perspectives. I just like to have a second iPad going, so if there's a chat from somebody in Zoom land, I can see that easily. Okay, so what I want to do is I want to show you how, if you can ask the right questions, this can often lead to new research directions or new ways of attacking things people have been looking at before. It is often extremely difficult to find what is the right perspective. If you have been trained in a certain way, you have an instinct to use those methods. If you want a successful career, you can become a technician and you can keep doing the same type of problems again and again. More valuable is if you go to a different field where they don't have the same skill set as you. So for instance, if you want to go off into finance, you'll be competing with students who have taken a tremendous number of classes related to that. And on a knowledge basis, you will be at a disadvantage coming from Williams. The hope is that you will have a broader experience, you'll have other ways of looking at problems, you'll have ways of seeing connections that other people haven't. And so because of that, you'll actually have an advantage. And then I will try to end with some open problems. We probably won't get to those today, but to just show you that this is an active research area. We have a wonderful research program that runs every summer here at Williams called the Small Program. If any of you are interested in doing that, I'm happy to chat further. I am the director, which means I get to do all the administrative paperwork. This is the dream we all have when we are young. But I also get to run a research group, which is a lot more enjoyable. All right. So out of curiosity, how many people have never done probability? Okay, not as a formal class, but at least seen some, hopefully in high school, where they've talked about maybe odds of events. And maybe if you're lucky, you took a calculus class where your teacher told you that the reason we care about integration, about finding areas under curves, is areas under curves are often probabilities of events. It would be a little bit strong to say if your teacher did not mention this, they deserve to be put on by the blackboard with a blindfold and you can guess the rest. It's probably a little bit too strong to say that, but not by much. You want to always be asking when you're doing a class, why? Why am I taking this? Hopefully it's a better reason than I need so many classes to graduate, and this is one of the ones that's going to check that box. You should be learning skills that are valuable. Why do we give you 3 classes on calculus? Well, hopefully calculus is good for something. And so if you haven't seen that calculus can give you areas under curves, which can give you probabilities of events, this has been a disservice to you, and we will fix that today. So we say x is a random variable with density p if the following is true. So p of x is non-negative, and it integrates to 1. And then the probability that x takes on a value between a and b is just the area under the curve from a to b. Now, We may not be able to write a nice closed form expression for this. Maybe P doesn't have a nice antiderivative, but formally we can still write this down. And this is one of the reasons we care so much. I'm assuming right now that my distribution is continuous. You can play all these games as to what is the most general P that you can look at. We're not going to play that game. For us, P is going to be nice. How many of you have done statistics? Want to guess what that is? Bell curve. If you can't use the phrase bell curve, what would you call it? Normal distribution. If you can't use bell or normal, what would you call it? No, it's not Laffer. Laffer is a different curve. There's another one you could do other than bell or normal. Begins with a G. Gaussian. Whenever you have this many names, it's probably important, okay? This is one of the most central distributions you will see in probability. So this is the Gaussian, where the density is given as follows. Two key facts about a distribution are the mean and the variance. Has everybody seen the concept of mean and variance before? Okay, so I'm not going to spend too much time on that. The other prerequisites I need is some very elementary combinatorics. N factorial is the number of ways to order n people when order matters. So the vice president is different than the president, is different than the secretary, is different than the treasurer. And choose k is the number of ways to order, is to choose k people from n when order doesn't matter. So you should think representatives in student council. Everyone is the same. And one way you can see this is if I have to choose k people when order matters, there's n choices for the first, n minus 1 for the second, all the way down to n minus k minus 1 for the kth. It's a little bit annoying, but we're starting off with n minus 0. So that's the n factorial divided by n minus k factorial. That's just the number of ways to choose k people from n when order matters. And then if I want to forget the order, if I have k people, how many ways are there to arrange k people when order matters? K factorial. And that's why if I divide by k factorial, that gives me the number of arrangements when order doesn't matter. And then the last one is Stirling's formula. And this can be proven mostly elementarily if you are willing to be a little bit fast and loose with some of the mathematics and the error terms, depending on how closely you want to prove this. This is telling you how fast n factorial grows. So whenever you see a complicated equation, you always want to ask, is this reasonable? So can somebody give me a bound for n factorial? N factorial clearly can't be larger than what? So give me an upper bound. Infinity, right? Definitely fine. Okay. Can you give me something that's finite now and is still going to bound n factorial? N to the n, because it's n times n minus 1 times n minus 2. So for every factor, just bump it up to n. So it should be smaller than n to the n. Okay, good. We see it's n to the n times e to the minus n. Good. It's smaller than n to the n. So this is at least a reasonable result. If I had n to the n e to the plus n, or n to the n square root of 2 pi n, I go, that can't be true. With a little bit of work, you can actually get lower bounds. You could look at all the values from n halves to n. There's n halves of them. So this would be at least n halves to the n halves. So you can play some games like this, and I'm not going to go through it now, but if you're interested, there are things you can do to get sequences of good lower bounds and upper bounds, and then can you try to get them to elementarily converge to this? But this is just telling us roughly, if n is large, roughly how big is n factorial? N factorial is one of the basic combinatorial objects we have. We want to get a sense of its size. Okay, so we've all seen the Fibonacci numbers before. They're given by the recurrence relation. Each one is the sum of the previous two. And I have to give you some initial conditions. So the most natural ways to start is 0, 1, 1, 2, 3, or 1, 1, 2, 3, or 1, 2, 3. And depending on what you're doing, sometimes one is a little bit better than the other. There are some formulas that are a little bit cleaner if you start with 0, but then some other formulas are not true. It's not a big deal. It's just annoying that you have to work. We will be doing it as 1, 2, 3, 5. And the reason we're going to do it this way is because now we have Zeckendorf's theorem. Every positive integer can be written uniquely as a sum of non-adjacent Fibonacci numbers. So basically you give me any integer and I can write it as the sum of Fibonacci numbers. I never use a Fibonacci number twice. And if I use the kth Fibonacci number, I can't use the k minus first or the k plus first. I can't use any of its neighbors. So for example, if I want to write 2012, what I do is I take the largest Fibonacci number at most 2012. I subtract it from 2012 and I see what's left over. I then take the largest Fibonacci number less than that and keep going and keep going and keep going. Does anybody know what this method is called? So at each moment, yes? It's not quite recursion. Computer science is a really nice name for this algorithm, where at each moment in time, you basically do the best thing you can and you just keep iterating. So sometimes mathematicians and computer scientists phrase things a little bit differently. This is the greedy algorithm. At every moment in time, I pull out the largest Fibonacci number I can, look at what I have left. It is extremely similar to recursion. Recursion is an acceptable description of what you're doing, but this is really the greedy algorithm. At every moment in time, you're doing what is best. It is possible, if you're doing things by the greedy algorithm, that what is best at every moment in time does not always lead you to what is best globally. Is somebody willing to share what they want to do for what their goal is for life? And I'm really hoping making billions and remembering your professors. Excellent, excellent goal. Strongly support becoming a multi-billionaire. Be the first trillionaire. Support being a multi-trillionaire and remembering your professors. What's the best way to get there? We want to maximize your happiness around the way. So should you be doing at every moment in college what maximizes your happiness at that moment? Well, I mean, given that you're all here, of course, that could be, probably not, right? So what's locally best may not lead to what's globally best. So doing what is best for you at this particular moment is not necessarily going to lead to what's best for you long-term. If people are interested in this, two of the papers I put as examples of great writing are by Pennings, Do Dogs Know Calculus? Do Dogs Know Bifurcations? And this is a wonderful example where if you're trying to go from point A to point B, going at each moment in time in the direction that minimizes how far away you are is not necessarily what's best. It's sometimes better to take a step backwards to have something else become available. And so I'm happy to go into more detail on stuff like that later, just trying to give you a sense of what's out there and things you can look at. Fascinating life lessons. So this is the greedy algorithm approach. And if I ever did this algorithm, and when I pull out a Fibonacci number, I look at what's left over, I pull out the next Fibonacci number. If these two Fibonacci numbers were adjacent, then I'm a moron. Because if they're adjacent, then their sum is a Fibonacci number, and I could have pulled that out. So it's a nice exercise. You don't have to hand this in. Try to make this proof formal. Is go through and formally write this up, and I'm happy to look at it. How would you prove this formally? This would just prove that a decomposition exists. Maybe it's not necessarily unique. So then you have to show that if there's another decomposition of my integer as the sum of non-adjacent Fibonacci's, it has to be the same one. I can't have two different ones. Does anybody want to conjecture when I first gave this talk? Yes, 2012, right? And I'm just using slides from 2012. If you have really good memory, you could probably go maybe even to the title slide, but I might have updated that, but not updated the example here. Okay. As a Bostonian, I will defer to someone from the audience. Anybody want to say the name of this mathematician? Close enough, much better than I would be able to do. So what he was able to prove is that if you look at the average number of summons in the Zeck01 decomposition for integers between the nth and the n plus first Fibonacci number, then it's approximately n divided by the golden mean squared plus 1, or a little bit more than a quarter n. Now, whenever you are proving a theorem or trying to study something, you always want to figure out where should you be looking, what should you be examining. I'm looking at how many summons do I have on average. That's a pretty good question to ask. But I'm not looking at all the numbers from 1 to x and letting x go to infinity. I'm looking at all the numbers from the nth to the n plus first Fibonacci number. And the reason is, when I look at my decomposition, if I'm in this interval, my first summand is going to be an Fn. If my first summand was an Fn minus 1, I can't have Fn minus 2. The best I could have would be Fn minus 3. You can show that that's not going to be enough to push you into this interval. If you want to live in this interval, your first summand has to be Fn. Okay? What this means is that in some sense, all of the integers in this interval are comparable. They all have the same first summand in the Zeckendorf decomposition. How many of you have ever heard the phrase comparing apples and oranges? So you want to try to do fair comparisons. If I'm trying to look at the average number of summonds, and one of my numbers is around 10 to the googolplex, and another number is around 2000, well, I might expect a typical element around 10 to the googolplex to have far more summons than a typical element around 2000. So I want to have a fair comparison. So what I do is I would look at from the nth to the n plus first. It turns out once you understand what's going on in an interval like this, you could actually extend this, and if you wanted to go from 1 to Fn, you can. And the reason is the Fibonacci numbers are exponentially growing. So if you just walk a little bit, it's much, much larger than where you started. Or if you go backwards a little bit, you don't have to take too many steps before things crash down. So the contribution, if I go from 1 to a little bit before this, to a few smaller ends, is so insignificant, I can basically just take care of it. So again, today the goal is not to go through all the details, but to give you a sense of what kind of issues are there. You have choice in what you get to study. To me, it's technically convenient to study it like this, because if I do it like this, all of my numbers are of comparable size. But you could start at 1. Has anybody ever done any advanced number theory? Okay, I'm not going to go into too much detail then, but if you do advanced number theory, you learn that it's better not to count all primes equally, but to do a small amount of discrimination. So you weight the prime p by a factor of log p. The logarithm function is very slowly growing. And so you're almost weighting everything the same, but it just makes the analysis a little bit easier. And then at the end of the day, you remove the weights. But it makes some of the things easier to put those weights in initially. Okay. So here is a theorem that as n goes to infinity, the distribution of the number of summons in the Zeckendorf decomposition converges to a Gaussian. When do you think this was first discovered? (2014). Why 2014? Okay, but look at the 2010. So the talk was given in 2014, but I was using a slide from earlier. And so I was going to a conference in New York City in May, and my summer research program didn't start until June. And so I knew my students would be able to prove this. So I announced the result before the students even looked at it. I said, I know they're going to prove this, and they're going to prove a lot more. I don't know exactly how far they're going to be able to push this, but my students will be proving this result, in a month or so. And so when you look at the data, does that look like a Gaussian? Yeah. If you have some statistical knowledge and background, there are a bunch of different tests you can do to see, does it really look like a Gaussian? And if you do all those tests, it comes back, yes, it's a Gaussian. Is there a proof? Hopefully, but it at least gives you some idea of what you might want to try to prove. The next one is a little bit more interesting, requires a little bit more notation to explain. So I have some integer m, and I'm going to write it as a sum of non-adjacent Fibonacci numbers. So I'm going to use I sub j to range over the indices. So I can never have 2 consecutive indices, okay? I know the last summand has to be n because my m lives in the interval fn to fn plus 1, and the largest summand is going to be fn. What I can do is I can look at the gaps between summands. How long do I have to wait before I get another summand? Well, depending on the number I give you, I can make it whatever I want. So you can ask, on average, how often do you have to wait? So how often do you think you have to wait 1 index before you get the next summand? So if I have F7, do you think I'd ever have F8 as my next summand in a Zeckendorf decomposition? No, because the Zeckendorf says it's a non-adjacent decomposition. So clearly, I'm never going to have a gap of 1 index. But I could have a gap of length 2 or length 3 or length 4. How often does each gap happen? On average, what's the average gap size? When I went to Disneyland with the kids years ago, they had a very low-tech solution to an extremely important question. How long is it going to take me from this point in the line to get to the point where I'm on the ride? That's something that they really want to be able to tell you accurately. So you can say, okay, it's a 30-minute wait. All right, I'll wait in line for that. If it's then an hour wait, you will have patrons who will be quite upset. And the real low-tech solution they gave is every now and then they gave somebody, they weren't misbehaving, my kids were angels, they gave them a red card. And when they got to the front of the line, they then handed the red card and they scan the red card. When they give it to you, they scan it when they come, and they know how long it took that card to go through the line. And by doing something like that constantly, you get some idea of the average wait times. If you are trying to understand waiting times between events, this is one of the most important topics we have in terms of managing customer expectations and making sure you can do all the jobs properly. So I'm just trying to give you a sense of where this material can go. Who are my computer scientists? Right. Have you talked about scheduling jobs? When you have a bunch of different processors, there's lots of different procedures you can use to determine which job gets assigned to which. Sometimes it's the rank hath its privilege. This is from somebody that we want to keep happy. They take precedence over everyone else. We will quickly put this stuff to the front of the queue. Other times I might want to just get a couple of things done quickly. Or this is a low priority job, so I can work on it whenever I have free time. You really want to be able to manage lines. Who has ever deposited money in a bank? 10 years ago, I wouldn't expect that this would be a difficult question. How many lines are there when you go to deposit money in a bank? 0?
Yeah, really.
But does each teller have their own line, or is there one line that feeds into the tellers? Which bank do you go to? There's one line. I mean, if you go to Spring Street, it's one line, and then whichever teller is free says next. When I was young, we did still have banks. No Venmo, nothing electronic. You had to physically go, and each teller would have their own line. The average wait time is going to be the same if each teller has a line or not. What's disadvantageous of having each teller having their line? Yes, you could have a high maintenance person in your line. And there's a really nice theorem that whatever line you choose, there's a high maintenance person in front of you. And you just get very frustrated, and you see all the other lines moving, and you get frustrated. I knew I should have gone to that line. And so the variance of the wait times is actually worse when you have each teller having their own line, because you can have one person get a terrible experience for a small set of people. Whereas if you have just everybody feeding into one line, who here has ever gone to a supermarket like Stop and Shop? Do you have one line to check out? Why not? Except for self-checkout, and then it's going to the first available. So why don't you have one line for checking out? It takes up a lot more space. So I'll let you think about that as to, should Stop and Shop and other supermarkets convert to just one line and then saying next with all these carriages and everything? Or are there advantages to having multiple lines? So whenever you're making a decision, you always want to be asking, is this a good thing to be doing? And sometimes the answer is inertia. This is based on an earlier day when this was the right thing to do, but nowadays it makes no sense. The QWERTY keyboard is a great example of something whose day has come and gone. We do not need a keyboard to slow us down in the 21st century, but we're stuck with it. So what I can do is, I want to study the gaps between summons. And so what delta is the Dirac delta functional. And the way you should view it is, it gives me a 1 whenever x equals whatever I'm subtracting, and 0 otherwise. So if I1 minus, if ij minus ij minus 1 is equal to 5, then when x equals 5, I'm going to get a contribution there. Think of it as putting a mass of size 1 at whatever this number is. So if I have a gap of length 5, this would give me a contribution at 5. But it would not give me a contribution at 7 or 9. Now, if I have 5 objects. How many gaps do I have between the 5 objects? Yeah, I have 4. And that's why I'm dividing by K of M is the number of summons I have, and I'm dividing by 1, and then this will give me a probability distribution. I'm putting a mass of size 1 over Km minus 1 at each gap. So every time I have a gap of size 5, I would put another 1 over Km minus 1. Every time I have a gap of length 7, I would put another 1 over Km minus 1. So this will just give me a nice function that I can work with to talk about the distribution of gaps. And what we were able to show is that it turns out you can show that these converge to a nice geometric decay. That the probability of having a gap of length 2 is the golden mean more likely than a gap of length 3, is the golden mean more likely of a gap of length 4, and so on and so on and so on. It's not surprising that the golden mean is coming, to play in the answer because we're dealing with Fibonacci numbers. One of the things that's worth remarking is certain theorems are easier to prove than others. If I ask you to do any type of averaging, the more averaging I do, the easier it is. If I want you to prove something for something in particular, it's often a lot harder. And so the first result we proved was that on average, the number of times you have a gap of length 2, of length 3, of length 4 converges to what you would expect. And then what we wanted to do is say, what if we just choose an M at random? What can you say about the gaps associated to that particular M? And then we could show with high probability, as n gets larger and larger and larger, almost all M have their gap distribution as close as you want to this geometric decay. I could give you the number M could just be Fn. And if it's just Fn, how many gaps are there? Nope, if I just give you M, my number M is Fn. How many gaps are there? None. What if I give you M is just Fn plus F1? How many gaps are there? Just 1. And so I can give you a couple of M's that will have very few gaps. We expect to have on average about 0.276 n gaps, 0.276 n summons. So if I give you M that has very few summons, that's an unlikely M to get. And so I don't expect every gap measure is going to be close to the average. I expect most will be very close. When you look at this, I'm old. I used to have good eyes. I now have to, have glasses to read things. Or I have to just have them, really far away from me. Can everybody see that this is a histogram? Can you see that the second column is the golden mean less multiplicatively than the first? Okay, so no one's eyesight is that good that you can look at this and you can see, oh, it's a geometric decay with the decay constant, the golden mean, or the reciprocal of the golden mean, depending on which way you want to run. So a big thing when you're doing writing is to try to figure out how do you want to convey something. You've probably heard the expression, picture's worth 1,000 words. A well-labeled picture's worth even more, right? So you can put down any picture you want. Which pictures are going to be particularly illuminating? A lot of times doing a log or log-log transform of the data leads to something that's much easier to visualize. And so what we did over here is, well, if there's supposed to be a golden mean decay, let me look at the ratios of the second gap divided by the third gap, their probabilities. And then the probability of the third gap of a gap of length 3 divided by a gap of length 4. And then the probability of a gap of length 4 divided by a gap of length 5. Each one of those should be the golden mean. And then what I did is over here is I plotted those ratios. And if you look for large numbers, gaps from 2 to up to about 20, those ratios are pretty close to the golden mean. To me, that is much easier to understand visually than looking at something like this and saying, well, how close is that really to geometric decay? I just can't see that as well. Then, of course, something interesting happens. But at some point, we're getting to the situation where we don't expect to have that many gaps of a large size like this. So 1 or 2 events can greatly influence. So who knows their baseball history? Did you have your hand up?
No.
Oh, no. All right. So in 2004, the Red Sox were playing the Yankees in the playoffs. And the Red Sox were down 3-0 in a best-of-7. So the Yankees only had to win one more game. In baseball, no team had ever come back down 3-0. Why do you think teams had never come back down 3-0? I'm sorry? Well, can somebody give me an estimate of the probability of coming back if you're down 3-0? I'm sorry? Well, give me an estimate. Give me a model and tell me this is my estimate of the probability. It can be a simple model that's wrong. What's the simplest model you can think of? They have a 50-50 chance. And so if they have a 50-50 chance, what's the probability that you come back down 3-0? 1/16. So I think on the order of maybe like 24, 25 times, a team had been down 3-0. Well, if you only expect a team to come back 1 out of every 16 times, you would only expect once or twice that you would have seen it in 24, 25 such series. So the data set is not large enough. So one series going one way or the other is going to have a huge impact on the data. So you've got to be very careful when you have small data that you don't let it be overwhelmingly influential. But can somebody give me a reason why a team down 3-0 might not have a 50-50 chance? Yeah, maybe there's a reason why they're down 3-0. They might be down 3-0 because they're not as good of a team. And so, the question is, what is the true probability? It's an interesting question. When you see something like this going on, something is happening over here that we should, understand further. Right now, I can't tell what's going on, but I do see it's happening deep down. That, in the beginning, things look like they're going very, very, very well. And then we might be in a situation where we have a small amount of data and we're trying to make extrapolations based on that. And so you always want to be very careful as to what you do. All right. The next one is a fun one. One of the papers I had you potentially look at is by, I think, Schilling on the longest run of heads. So if you toss a fair coin, or even a biased coin with probability P of heads, you can ask, on average, what would be the longest run of heads? Or equivalently, what's the longest gap between tails? Well, all these questions are essentially the same. And it turns out the result is remarkable. It is related to the exponential of a nice function. I don't really want to go into all the details here, but this looks like a function that somebody would make up to just test you. Do you understand the chain rule in calculus? This is the exponential of an exponential. This is a place where it actually arises naturally. And it turns out that the same thing is going on here. If you want to look at typical M and you want to ask how long in the Zeck01 decomposition, what's the longest I might have to wait before something happens? And so for a lot of things in the real world, you want to understand waiting times. You might want to understand how long might I have to wait before something happens. Okay. And so what I want to do now is talk a little bit about some of the mathematics that's needed to prove these results. So there are a couple of ways of describing this. I prefer to do this using cookies. So imagine we have C identical cookies and P distinct people. Okay, so we will assume that we can distinguish who you are, but we can't distinguish the cookies. If you have children, that's not necessarily a good assumption. They will find minute differences, but we will assume that these are idealized, and we will assume that these are not engineering graduate students. We will assume these are math grad students, so the professor actually knows who they are, not lab assistant 1, lab assistant 2, lab assistant 3. I want to know how many ways can I divide the cookies among the people? And the answer is C plus P minus 1, choose P minus 1. And there's a really nice way to prove this. So a lot of combinatorics comes down to telling the story, finding a way to look at things. When I was a graduate student at Princeton, somebody had asked me something related to this. And this led to my creating a math riddles page, which has been used in schools all over the world. And it was nice that years later, I was able to use that to come up with a new way of proving Zeck01 theorem and so many more results with students. So does everybody know who Cookie Monster is? Yes? Does everybody know who Oscar the Grouch is? What was Oscar the Grouch's original color? That is the green guy. But he was not originally green. I think he was originally orange. I'm going to deal with the original classic Cookie Monster who is always up eating cookies. For him, cookies are not a sometimes food. He is game on for eating cookies. Okay, so imagine we put C plus P minus 1 cookies in a line, and Cookie Monster comes and eats P minus 1 cookies. Well, if he eats P minus 1 cookies, how many cookies are left? C. And it turns out that if he does this, it's going to divide the cookies into P sets. So let's see an example. So imagine we have 8 cookies and 5 people. Since this is a Fibonacci talk, I chose 8 and 5. Cookie Monster shows up. So here comes Cookie Monster. And now Cookie Monster eats P minus 1 cookies, so Cookie Monster eats 4 cookies. Everything up to the first eaten cookie goes to the first person. So the first person gets 2 cookies. How many cookies does the next person get? 0. And the next person gets 2, the next person gets 3, and the last person gets 1. So this might bother your sense of fairness that one of the people got no cookies. If that bothers you, we can actually fix that later. For now, we will allow an inequitable distribution of cookies. There is a 1-to-1 correspondence between the number of ways Cookie Monster can eat 5 cookies from 12 cookies, and how many ways can we divide 8 cookies among.
Why did we start with 12 cookies?
Because we want to look at C plus P minus 1 cookies. And so when we do that, when Cookie Monster then eats P minus 1 or 4 cookies, oh, sorry, I might have said 5 cookies. When Cookie Monster eats 4 cookies, he's putting in 4 partition points. Everything up to the first partition goes to the first person. And then once we have that last partition, we get the partition that we got coming to it, and then 1 partition after that.
When did you distinguish the order of that?
Doesn't matter. This is why it's a N choose K problem. The order in which he eats the 4 cookies doesn't matter. Is Cookie Monster needs to choose 4 cookies to eat. And whichever 4 cookies he chooses, he's putting up 4 partition points. Everything up to the first partition point is going to be given to the first person. Everything from the first to the second is going to be given to the second person. Yes?
Who would eat the first 4 under no partition?
So if he eats the first 4, the first person gets 0, the next person gets 0, the next person gets 0, the next person gets 0, and the last person smiles and gets everything. Okay? So there is a 1-to-1 correspondence with how many ways Cookie Monster can eat P minus 1 from C plus P minus 1 cookies, and how many ways we can divide C identical cookies among P distinct people. And this is a nice simple combinatorics problem. How many ways can you eat? How many ways can you choose P minus 1 cookies from C plus P minus 1 when order doesn't matter? That's just the binomial coefficient C plus P minus 1, choose P minus 1. And we're done. So this is a great way to use some combinatorial knowledge to get a result which will be of use for us in a moment. You might have seen this if you've done combinatorics. It's often called the stars and bars problem. That's the more standard way. I like to look at it as the cookie problem. All right. Now, in a math research paper, they really won't let you talk about Cookie Monster. So we do it more formally. Imagine we have a bunch of non-negative integers, x1 plus dot 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 plus xp that sum to c. How many ways are there to do that? Well, that's exactly the same. It just x1 is how many cookies the first person gets, and so on and so on and so on. So it turns out that this has an immediate application to the Zeckendorf problem. So let's let p and k be the number of integers in the interval fn to fn plus 1 that have exactly k summons in their Zeckendorf decomposition. So this is a more involved sequence of numbers than you've typically seen. This now has 2 indices. So it's going to be a little bit more complicated. I want to see, is there a formula for how many integers have exactly k summons? It turns out there is. You can do this not just with Fibonacci numbers, you can do this more generally for other sequences. And for those other sequences, you no longer have nice formulas like this. So this formula is only going to be nice and clean for the Fibonacci's. and for other very simple sequences, it will not be true in general. And this is one of the real dangers of looking at a simple case and building your intuition from the simple case, is you might then think, oh, it's not going to be so bad to generalize. So let's try to come up with a proof. So imagine we have an integer between fn and fn plus 1. We know its largest summand is fn. And so imagine I have some decomposition, I1, I2, ik minus 1. These are my different indices. Okay? At this point, you should just be trying to follow the big picture. You should not be trying to do the algebra, in your head right now, or looking at all the details. You should basically say, okay, I get roughly what Professor Miller is saying. If it's not clear, ask me and I will elaborate, but you should not be trying to follow all the lines of algebra live. Nor should I be trying to do algebra live with the camera on. Okay. So now, let me just make sure that this is recording, because did it say recording on when we started? It's a little bit late to be checking. It just said recording. So now I have my summons, and I know the smallest I1 can be is 1, and I know the last one has to be k, and I know each one of these gaps has to be at least 2. Imagine I wanted to do the cookie problem, and I have 8 cookies and 5 people. Did it bother anyone that some people got no cookies? Was anyone bothered by this? Okay, you're a good person. Okay, you can go home and you can feel proud. For the rest of you, no, I won't say that. So what can we do to make sure that no one is sad? What constraint could we impose? Everyone must get at least 1 cookie. And so rather than dividing 8 cookies among 5 people, why don't we just take 5 cookies initially and give everybody a cookie? And now we have 3 cookies to divide, where I don't care if somebody gets none of those extra cookies, everybody got at least 1 cookie. So really, if you want to divide 8 cookies among 5 people where everybody has at least 1 cookie, it's the same as dividing 3 cookies among 5 people. It's very easy to put in lower bounds. It's unfortunately very difficult to put in an upper bound. What would an upper bound mean? Right, is no hogs. We're not going to let anybody have more than 4 cookies. That's excessive. So putting in upper bounds, it turns out the mathematics is much, much harder than lower bounds. Lower bounds are easy. So if you look at the indices, I know ij minus 1 has to be at least 2. So what I can do is I can define, d1 is going to be I1 minus 1. How long did I walk from 1 to I1? And then dj is going to be how far I had to walk from ij minus 1 to ij minus 2. So basically, I'm throwing away the amount I know I have to walk. I know I have to walk, at least 2. And so I'm going to throw that away. So now, how small could dj be? What's the smallest dj could be? So d1 is I1 minus 1. So what's the smallest d1 could be? 1. Why 1? If that's 1, then that would mean I1 would have to be 2. It's 0. The smallest I1 could be is 1. So it's possible that d1 could be 0, it could be 1, it could be 2, it could be 3. Yeah, because we know what's the smallest ij minus 1 could be. Nope. The smallest between 2 adjacent indices in the Zeck01 decomposition. What's the smallest that could be? 2, right? You can't be adjacent, so the gap has to be at least 2. So I then subtract the 2. Oh, so dj is at least 2. I'm sorry, dj is at least 2 minus 2, so dj is at least 0. So I now have a bunch of non-negative integers, d1, d2, d3, all the way up to dk. These are all non-negative integers. If you do the algebra, and we will not do the algebra in public, you get that their sum is n minus 2k plus 1. I'm looking at a bunch of integers that are non-negative, and they sum to n minus 2k plus 1. Does this remind you of anything? So I want to know how many ways can I choose non-negative integers d1 through dk such that they sum to n minus 2k plus 1. What does that remind you of? What have we done today that this is similar to? It's related to n choose k. What is this related to? Not the Fibonacci sequence. So I have a bunch of integers, non-negative, and I tell you that they sum, and I want to know how many ways can I choose non-negative integers that have a given sum. It's the cookie problem. It's exactly the cookie problem. The number of ways you can do this is just going to be n minus 2k plus 1, the number of cookies, the number of people minus 1, I have k people, choose the number of people. And when the algebra simplifies, you get n minus k, choose k minus 1. So the number of integers between fn and fn plus 1 that have exactly k summons is this. Okay, that's not so bad. We have a nice explicit formula. What you then do to finish the proof is you have to know a little bit of combinatorial identities and whatnot, is you can basically say, well, let's sum over all possible k. And you show that an integer can't have two different Zeckendorf decompositions. So it either has no summons, one summon, two summon, three summon, etc. Everybody has to have at least one summon because they have to have fn. No number is ever counted twice. There's no number that has two different Zeckendorf decompositions. Is it possible that there's some number that has no Zeckendorf decomposition? Yes. How many numbers are there from fn to fn plus 1 where I include fn and I don't include fn plus 1? How many numbers are in that interval? Nope. I'm going from the nth Fibonacci number to the n plus first. So if I go from 5 to 8, how many numbers are there from 5 to 8 where I include 5 and not 8? I'm sorry? Which is 3, which is the previous Fibonacci number. How many numbers do I have in this interval? It's fn plus 1 minus fn is fn minus 1. If you sum this over all k, you actually get fn minus 1. And that proves that every number has to have a Zeckendorf decomposition. Every number is accounted for. No number is ever counted twice. So it's a nice exercise to prove. Now, you have to be a little bit careful. Can anybody tell me how many ways are there to choose 3 objects from 2? 0. So it turns out you have to be a little bit careful as to what do you mean if the denominator, if the bottom is greater than the top. We interpret it as 0. With advanced math, there's actually nice explanations to why that's true. So I will just quickly go through, we've got about 2 minutes left, the proof that my students did. So I basically said, just use Stirling's formula. We know the number of times you have exactly k summons is n minus k, choose k minus 1, and just show that that converges to a Gaussian. And so I'm not going to go through the algebra here, but they just started off, and we played some games. It was a little bit easier, I think, to study by shifting things over a little bit. And we just shifted everything by ones. We looked at n plus 1 to n plus 2. And so we just calculated, here's how many times you have exactly k summons. We divide by the number of integers there on the interval, which is fn, and then we just have to show that this converges to a Gaussian. And so you just start doing some algebra. And I knew the students would be able to do the algebra. You know, there were a couple of mistakes a couple of times. At some point, we start taking logarithms, because whenever you have products, logarithms are nice. You start expanding things using Taylor series. You then do more expansions with more Taylor series, and you keep simplifying, and you keep doing more and more analysis. All of this is pretty straightforward, very easy to make mistakes, which happen numerous times. You keep expanding, expanding, expanding. Turns out you only have to keep the main terms. The big O means that these are smaller terms. And eventually you get to a square, which means you've finished your proof. And so it really was a follow your nose proof to get Gaussian behavior. The question then becomes, does this hold in graded generality? For which recurrence relations will you have something like that? And so we will continue on this later. I will send you an email about next week. Stop recording.